technological difficulties.
George Wolcock.
Are we on?
It's going to the wrong meeting thing that we'll have to do. I'll post where it's going to.
Good afternoon, everybody. Sorry for the delay, but it wouldn't be a McLean meeting if we didn't have a technological issue at the beginning. Those of you that were at the January meeting may remember we had a few little issues in the room upstairs, but we got there in the end, combined technological knowledge. We worked it all out. Anyhow, great to see you all again. Thanks for coming. At the back has told me that the microphones aren't working that well. At all? Not even a wee bit? You can hear me in the front row. I'm not normally that quiet anyhow, so I can raise the volume, but just for further speakers to be aware. And we also need to make sure that it's being received on the YouTube, but I'm sure the text will start coming in. Anyhow, just a couple of little things. First of all, have we any new members here today? No, not one. I've got me badges. Just to bribe. Oh, well, that's a shame. But I know we've had a very good few meetings of new members signing up between our appearance at Astrofest, the Practical Astronomy Show. We've had quite a few good sign-ups, which is keeping the membership on a nice even keel. Of course, the issue is then that we retain our new members, and we would like to do that and make sure that what we do is interesting for all of them. Just because if I leave it to the end, I'll forget to say it. The next meeting is on the 4th of June here at the Institute of Physics. It's the occasion of the George Olcott Lecture, and I am happy to announce that David Boyd will be delivering it. And the subject matter will be? I thought it might be about something to do with spectroscopy. A spectroscopist's journey. Okay. Right, first up is I'd like to ask our treasurer, Graham Winstanley, who is going to address you with regards to the new members' rates. Graham.
Right, well, I'll just be very brief and to the point. And the trustees have agreed that there will be no changes to the membership subscriptions for the coming session. Any questions? All right, that was brief.
He said he'd be short and sweet, and he was. Okay, I call upon Professor Dr. Jeremy Shears, our BAA paper secretary, to talk about papers accepted for the journal. I'll sit here this time.
Indeed, we've had a flurry of submissions to the journal, so we've actually accepted for publication this afternoon 7 papers. So I'll read those out. William Evan McFarlane and Nova Aquili 1918 by Chris Hicks. Studying OJ287's puzzling colour variations and searching for its host galaxy with a backyard telescope by Mark Kidger, Paul Boltwood, David Boyd, Gary Poyner and Esteban Reiner. The Opposition of Jupiter 1961 by Richard McKim. The Total Solar Eclipse of 2026, August the 12th, by Peter MacDonald. 2 British independent discoveries of the 1946 eruption of T. Corona Borealis, by myself. Observing the shadow transits of Mimas and Enceladus, an 1890s mystery solved, by Richard McKim. And last but not least, The Brighter Comets of 2023 by Jonathan Shanklin.
Thank you very much, Jeremy. So are we approving these submitted papers? They're approved by council, just in case anyone wanted to particularly disapprove. All right. Moving on then, I call upon Dr. Richard Miles, who is going to talk to us now about eruptive comets, a comparison of comets 12P Ponsbrooks and 29 Schwarzmann-Wachmann. I think everybody knows Richard, don't they? Maybe I need a little introduction.
I'll be telling you about my background.
Oh.
I'll cover that.
Oh, okay. Right, you need to stand here with this issue with the microphones.
Well, otherwise people at home won't be able to hear.
Oh, is that the reason?
Even though the microphones don't help in here,
Okay.
people at home can't hear you.
Oh, I was going to walk up and down the aisle and just around.
I will stick your shoes to the floor because you have to be here for it to be picked up to be sent to our members that are watching in YouTube.
That's lovely.
All right. Thank you very much. Let's have a round warm of applause.
I think I'm due to start at 6 o'clock, so so that means I've got 17 minutes to talk to you before I show you any more slides, right? Sorry, it's a captive audience, Paul, so you won't be able to get away. Does anybody know what an eruptive comet? Anybody know what an eruptive comet is? I thought, as I was going to give a talk to you all about it, I thought I'd look on Wikipedia. Anybody? And if you do that, you will find that eruptive comets don't exist, right? So this talk, at the end of this talk, what you're going to realize is there is such a thing as comets that undergo cryo-eruptions. They're not volcanoes, but they are special. Right. So it's a long story, and it starts 18 years ago. And I'll explain a little bit why I got into it. And 18 years ago, on October 24th of 2007, there was an enormous outburst. Now, if you look up outbursts, everybody knows about outbursts of comets, and that's what they've been called. Okay. And it was Comet Holmes, 17P Holmes, it outbursts. And only a few days later, we had a BAA meeting in Burlington House, and we all paraded outside into Piccadilly stood on the center of the dual carriageway, or whatever it is, and looked up at the constellation of Perseus, and we saw an extra star in the constellation, second magnitude. That's because a 16th magnitude comet had suddenly brightened 400,000 times. And it really grabbed my attention big time. And there's a photo of us standing on Piccadilly, pointing to the new star in Perseus. And I thought, wow. And 2 weeks later, I'd submitted a paper to the RAFs, I think, because I have to confess, my background is a research scientist. That's what my day job was. I've retired now, and I do astronomy full time. And the fact that happened just grabbed my attention. All of what I'd been taught in university and so on, suddenly it all meant something. And I thought the astronomical world, the professional astronomers, would likewise realize that this was a watershed moment for astronomy, and that the world, the astronomical world and solar system, small system bodies would be looked on in a different light. I sadly, here we are 18 years later, and that's not the case. So what happened in that intervening 18 years? I'll run through some of it. It's great that I've got this extra time. Oh, is that right? Oh, okay. So I've always been involved in the Fawkes telescope, even before it even existed. I've been, actively involved and going to meetings and so on. And the Fawkes telescope sort of got off the ground in the noughties, and so by 2007 it existed. But I think it was I was the actually I was the president of the BAA in. Oh, I just finished, hadn't I? No, I was just still the president. I had a few more days to serve my term, and where did I get to? So I didn't have any access to the Fawkes telescope. It was still too early days. But by 2010, 3 years later, 2.5 years later, I was, for my sins, I was able to use the Fawkes telescope in real time for half an hour. And we had, during the time I was president, we had a Liverpool meeting, that's it, where we actually, and Nick knows this, actively linked in, and we took the first remote observation in real time of, what was it? It was quite a, no, I don't think it was an outburst, but it was a comet, yeah. But in 2010, February the 3rd, I had a half-hour stint on it. And I'm an asteroid person, really. I just don't look like it, but I am. And this converted me to comets in a big way. Because when I looked up what to look at, what to point this dirty great telescope at, I found out that the day before, comet 29P Schwarzmann-Wachmann had a major outburst. And it was a really big one. It was really one of its biggest we've seen in the last 20, 30 years. And I was able to take images through different filters on that. And that's where I started to get involved. And I was thinking, the astronomers hadn't realized how important that Holmes outburst was. And here was another one. And it was like a calling, this had happened. And eventually, it ended up as a paper in the professional journal Icarus, and so that was that. So the next big step was when Dill Fawkes sold his Fawkes telescopes to who was it? Wayne, not Hawking. He was a deputy in Google, deputy manager in Google, and he bought the Fawkes telescopes. But he had a great idea to set up a network of 1 meter telescopes and 0.4 meter. And so come 2014, that's when it became possible to schedule observations in advance. And it became possible to monitor comets or asteroids as to find out what they're doing. And that started up. And actually, there were 2 great observers as 29P. It was Kevin Hills and Jean-Francois Soulier in that year. And that's when we started what we call Mission 29P, which is the BAA's sort of extra effort to make up for the fact that NASA, in its wisdom, has decided, although they've had applications to send space probes to 29P from 2 renowned groups in the States, it's never become a possibility. And the reason why we're doing Mission 29P is I was told that there's not enough data, not enough information known by the professionals to justify it. So we're trying to gather as much understanding of the comet as possible. So we've been observing as often as we can, and by now, it's no good observing once a day. You've got to observe 24/7 several times a day from different places around the world, and that's what you'll see. That's what we've been doing. Okay. What happened next? Yeah. So George Fayassi, the late George Fayassi, was a member of the BAA, and I, in that was 2012, we wrote a paper for Icarus, and this is the journal. Icarus, it's the solar system journal for the, it's part of the AAS, the American, and it's the Division of Planetary Sciences journal, essentially, at that time. And it was called on liquid phases in comets, and it was to try to point out, and this is not outburst, to point out that even just looking at the physics of it, that you would get liquids, and it was most favored in more distant comets at around 5 or 6 AU, and the liquids would be the hydrocarbons. So we looked at methanol, we looked at water, and this was a theoretical analysis, right? It's a modeling of that. And again, nothing happened after that. So come 2014, and we'd started mission 29P, what I did was I looked back at all the Minor Planet Center data on 29P, and I looked and thought more about the chemistry. Now, this is where I'll say about my background. I did both my degrees at Bristol, and I'm a physical chemist, and my supervisor was Professor Everett. Now, Everett was a great man. He did great things in the war, but he also was one of the leading lights in spreading the word in chemistry of thermodynamics, and he wrote a book called Introduction to the Study of Chemical Thermodynamics. And he also wrote a book on study of porous media, and comets are porous media, finely grained porous material. And what I did is I wrote 3 papers, and there are 3 papers in this one copy of Icarus that came out in 2016, and it's almost a quarter of the entire volume. And those papers, the first paper was the results of those first observations of 29P on February the 3rd, and the follow-up we did to it. And I haven't got time to go into detail. There was a second paper which took all the Minor Planet Center data and the observers' data, and the observers are all acknowledged in there, 200 odd. And that came up with what seemed to be a rotation period of nearly 58 days for the comet, for the nucleus. So, but the one that really I'm proud of is the one which is, let's read, it's called Heat of Solution, a new source of thermal energy in the subsurface of cometary nuclei, and the gas exsolution mechanism driving outbursts of comet 29P, Schwarzman, and other comets, right? So there were a list of 17 comets in that, which I said are special because they outburst without fragmenting. Now, Holmes exploded 400,000 times. The orbit didn't really change. The comet is perfectly fine afterwards. This is not a fragmenting body getting too close to the sun. And 29P, well, I'll start to show you some slides, but that's not 29P is in a circular orbit. So here we are trying to convey to the professional community that there's something worth studying here. But the way it is that amateurs are much, much better placed to observe 29P. The professionals can't do it. And they just do, say, use the HST or James Webb, and they just get a couple of hours on it, and that's it. So Now, coming back to Professor Everett, the thing about it is that that branch of science really came to the fore in the first half of the 20th century. And we are now in a situation where we're losing touch with our heritage, our scientific heritage, where people, physical chemists actually wrote the textbooks. And the ignorance in the community of the professionals, I'm afraid, they have not tried to understand the subtleties of thermal heat transfer in a complicated body. And the most important thing is, and this was I was warned by Jonathan Shanklin, the previous section director for the comet section. This was a week after Holmes had erupted. He said, because I said, there's liquid. There has to be liquid below a crust inside the nucleus. He said, the professional astronomers nobody will accept that you've got liquid, for example, liquid water inside a comet. And that's what really we've been up against for the last 18 years or so. Now, coming now back to the Forks, and the new network is called the Las Cumbres Observatory. And we have had for 4 or 5 years now a group of people from various countries who participated in what we now call comet chasers. It's a group, some of them are teachers, and Helen Usher is the sort of prime mover of comet chasers. And we actually have access, and people belonging to this group take the images, they schedule them and get the images. And they're doing that in parallel with lots of amateurs around the world. So I think I'll finish off on that preamble, and I'll say a little bit more. The one last thing to say before I show the slides is that the main reason why the professionals are hesitant to take a leap into the dark is that they think they know what the mechanism is behind outbursts of comets. And they came across a relatively obscure paper in physical chemistry from 1974 about a thing called amorphous ice. So amorphous ice is I'll just try and draw a picture of it. When the solar nebula was condensing out of a molecular cloud and forming, there were different temperature regimes, so closer into the central star or further out. And if you go further out, the temperatures could get very low. And so if there's, for example, a molecule of water flying through space looking for a home, if it hits a solid surface, it sticks. The sticking coefficient is virtually 1, and it stops. And it's at a very low temperature, 50 Kelvin. And then other molecules over many millions of years will also, and it builds up what's called amorphous ice. So it's really pristine. It's the definition of a pristine comet if it's got amorphous ice. Now, amorphous ice has never been detected by the professionals in all this time in any comet. There's no observation of it, but that's understandable because you need to go there. And when they went to 67P Chury, Yumov, Gerasimenko, the Europeans, they went to a comet which was so eroded and so heat treated, it had been burnt to a crisp, and all these volatiles and any amorphous ice had disappeared completely. Right. So when I knew that 12P Pons Brooks was going to be coming to perihelion, it was on my list of comets. Was it going to perform? Was it going to outburst? And I thought to myself, if it really puts on a show, then at last, the professionals will realize it's not just a weird, strange, single, unique body sitting trapped between the orbits of Jupiter and Saturn that is doing things they can't explain. This is a Halley-type comet, which is in it's in an orbit which is quite normal. So why should why should it do this? I'll start my first slide. I've added Halley to this because it's, we all understand Comet Halley. It's in our history. And these two comets, 12P and 1P Halley, have got an almost identical period, and they come in closer to the sun than the Earth, so they get heated, and then they disappear to sort of level with Pluto, roughly, around about 34, 35 AU from the sun. And so these are two comets I'm talking about tonight, which are very, in some ways, from their orbits, are very dissimilar. So this is why I think 12P is such an interesting object, because it opened the possibility of showing that 29P was not one singular thing. It was one of a group of objects. And what I said in the paper is I actually hypothesized that the reason why they do this is they have to have a slow rotation rate. And that if you've got a rotation period of greater than 5 days, then there's a chance. And the reason is that, and again, it's in the paper, the theoretical side, all of the action that creates this cryomagma below a crust happens on the night side, on the cold side. So you have to have a slow rotation period to have physical chemistry taking place. So the orbits, if we look at the orbits, there's 29P. As I say, it got trapped where it is. It's at what's called the sort of gateway before they become a Jupiter family comet. It got there by gradually being perturbed by the giant planets like Uranus and Neptune, and it moved sort of from the Kuiper belt and got closer and closer. So that's why it's been there in the same orbit roughly for at least 1,000 years and probably several thousand. So bear that in mind, and we'll come back to the amorphous ice story at the end of the talk. Right. 12P was Jean-Louis Pons, who discovered 37 comets. He's got 5 periodic, and 3 of which have his name on. And Pons-Brooks is one of them. It was discovered, again, it wasn't known to be the same comet, by William Brooks accidentally, although he was looking for comets. And he discovered it about Mag 10. And it was only a few weeks after he discovered it, it started to outburst. The middle drawing is by George Alcock. And you notice the dates here are 71 years apart. It's the orbital period of the comet. And that George, he actually drew that well after lots of outbursts and after perihelion passage. Right. So we're looking at these two comets, and we're looking at Comet Halley. Now, Comet Halley is also an outbursting comet. In 1835, it actually, and Sekanina in the States has written about this. He's shown the drawings of Comet Halley looking like Comet Holmes back in 1835. So these are images of these 3 comets, and you can see the similarity between what Halley did. Halley didn't outburst when it had its perihelion passage in 86. It did so 5 years later when it was 14 AU from the sun. So you see these outbursts are happening far from the sun. It's nothing to do with the sort of melting of the surface of the comet by being too close to the sun. Now, I've also included an image of 12P, which was taken about 3 days after a very weak outburst, what I call a mini outburst. And it's actually, you can see it's an asymmetric. We really needed something a little bit more energetic than that to be able to compare it in the same way. But I'll go on and show you what it looked like once 12P had a major outburst. Now, in the COBS database, if you look at what happened, it's now on its way back to a deep space. But the COBS database looks like that, and you can sort of see the noise of where the outbursts happened. And the first one was on July the 20th. Nick James has been is part of this story, and I'll tell you a little bit why later. But here's I think, well, it's on the Comet Section website. So I've presumed it's yours, Nick.
Yeah, I mean, this will be in the archive as well, but yes,
Yeah, there's an article. You put an article out. Yeah. There's another picture here by Ian Sharp, and this is the November 14th. That was the strongest outburst of all, and this is the sort of behavior. And what you're seeing is a sort of central dust cloud and a gas cloud expanding beyond it. And as you see, if you look inside the dust cloud, you see a slightly strange sort of condensation, or whatever you want to call it. And I'll talk about that in a while. Now, this particular November the 14th event was discovered by Nick. He was the first observer to detect it actually doing things. And a few other people joined in. And this is the light curve of the rise towards maximum of it. And what you've got here is, I'm not sure if I can, you've got this increasing, this acceleration in the light curve is almost certainly due to the fact that when material is ejected out into space from beneath the crust, it sort of disintegrates. And half of it, or a good portion of it, it might be even more, is composed of volatile ices which volatilize quickly. You know, things like carbon monoxide. And this gas that's produced inflates the dust cloud. It's like as though it's inflated from the inside out. And that's why you get this spherical, the gas is just escaping isotropically in all directions. And as it does so, it actually what it's doing is it's accelerating the expansion rate of the dust cloud. It's accelerating the particles. And initially it accelerates the smallest particles most rapidly. So then what happens is the cloud, a point comes here, and it's only after 10 minutes or so, where the gas pressure of the gas has got so low, it can't actually accelerate. It doesn't impinge on the particles of dust enough to accelerate it. And the gas is going out. It's moving much, much faster than the dust. But in this case, it accelerated it to over 300 meters per second, which is decent. And that's all happening in the first 10 minutes or so. In fact, this one is probably lasted a little bit longer because Nick didn't get onto it early enough. Shame. No, you did really well to actually catch this. And Peter Carson, of course, is down there. He got a set on there, and Guy Wells, and that helped to define the shape of the curve. Well, this talks about comparing this comet with 29P. So this is the sort of curve you get if you see 29P having a strong outburst. There we go. So you see you have the same process at the beginning. 29P is slightly different in the nucleus is bigger. So part of the acceleration is after the expanding cloud extends beyond the edge of the nucleus. So now this happened for 412p, this happened July in 2023, and Comet Chasers were going strong, and we got onto it very early on. So you see these images, sorry, the plots here are all, the ones in blue are all taken through a 2-meter telescope. And what I've done is I've just measured the brightness in a very small aperture. It's only 3 arc seconds across. So that way you can, and what we were trying to do as a team is to try to, as it faded and it entered this quiescence, we thought, great, we'll be able to watch it as it rotates. And because, you know, the different shape will cause a modulation in the light curve, and we'll be able to see what's going on. So you know, we really hit this hard, and we got lots of runs over different nights. And could I get a period out of it? I couldn't. And in the end, what I discovered was the only thing that was causing it to vary was the seeing at the time the images were exposed. So one of the techniques you can do in photometry of comets is you can measure its brightness in apertures of different sizes. And the advantage of that is you can then extrapolate its brightness down to 0 radius. You can only measure with a 3-pixel radius aperture, but you can extrapolate further back. And that's the technique of trying to find how bright's the nucleus on its own. And that's what I did with the data from the 2-meter telescopes. And this is there are 3 sort of groups here, and this was an attempt to look at different parts of the period of quiescence. I'll just go back to the previous. You see where I've circled in red that quiescent period. We've got the 3 different, and the best one is the middle one. That went on for 17 days, right? So going back to the plot, this is the plot of our attempt at measuring the intensity of the light reflected by the nucleus alone by extrapolating what's called the growth curve. And you can see how dependent it is on the seeing. Right. Now, the ones done closer to the outbursts are slightly more elevated, but they're following the same trend. And likewise, in September the 8th onwards, there was an outburst on September 4th. So that is also contaminated it by more dust close to the nucleus. So now the amazing thing about this, we obviously can get a measure of the size of the nucleus. And it's probably somewhere between 14 and up here and around 17 kilometers, because the extrapolation is not necessarily, that's as far as you could go in that, but it probably levels off a very small FWA term higher. So you've got a 15-kilometer nucleus. Now, the amazing thing about this data is if you just take those blue line, look at the scatter of the data points. Now, these are 9 different dates in that period. And there were several taken on the same day, say 6 hours apart. And none of them are showing anything more than about 5. The scatter on that is normally, for an asteroid, is enormous because of the elliptical shape or whatever of the asteroid. But the fact that there is virtually no scatter, and there's a scatter and uncertainty in doing the extrapolation to get the intercept, to get the nucleus magnitude. So this thing is absolutely billiard ball, virtually. It's spherical. It's like, right, now, quite the opposite to 67p, which has been eroded into 2 bilobal strange things. But this thing is unique. Now, we've done a lot of work on 29p over the years, and we've tried this same process of trying to measure the characteristics of the nucleus by extrapolating, this intercept, and you plot it as in this case against the seeing. So this next plot is showing sort of similar data for 29p. So the seeing is, I'm using a different factor, but it's similar. It stretches it out more effectively. But this is now the scatter you get, and these are runs done on 5 different apparitions. So they start in 2014 and all the way up to 2022. So this, there's sort of 50 data points. And remember, you have this difficulty of extrapolating. Notice it's not nearly as steep. That's because 29p is much further from the sun. It doesn't have the problem of being so active close. It's not outgassing all in quite the way that 12p was. So seeing has less of an effect, and we get this size, and that size is very close to 60 kilometers across. Now, one of the outputs of the mission 29p is that we've been able to actually get the orbit of 29p properly understood. So we're able to predict when it will occult a star. And we've had 5 successful occultations, 2 of which were multi-chord. And I'm a co-author on a paper that Mark Bowie is writing on those results. And it's very clear that the shape from the occultation is not spherical entirely, but certainly the oblateness is greater than 0.8. A sphere would have an oblateness of 1. And so this is another example of an object that's been outbursting intensively for many centuries, and it's still a relatively circular, spherical, oblate spheroid. Right. I'll just quickly go back now to 12p and show a little bit of the BAA comet section results later in the apparition. It reached 12p reached perihelion in April of 2024, and this is the data from the comet section, just plotted as I think a magnitude over time, and you can see how it's the base activity was brightening and so on. Now, I'll show you a plot now of the comet chasers data from the 2 meter and the 1 meter, and actually there's some 0.5 meter as well. So you might not be able to see it on there, but actually Nick discovered 2 outbursts, 2 significant outbursts. He was after his November 14 success, lo and behold, about 16 days later, there was another very strong outburst. So that's one thing I'd like to point out. Notice as well the, where are we? October 31st, November the 1st. Now this is the benefit of having lots of observers. We actually saw one outburst that was followed less than 24 hours later by another. Now for 29p, that happens all the time. It's called a triggered outburst. It's only strong outbursts that will make it happen. And the idea that an enormous cryo-eruption provokes a further eruption is really very difficult to explain if you think that amorphous ice is the source of your outbursts. So the next is a table of all the outbursts that 12p did. It had 16 that I know of. There were 2, the ones in red at the bottom are 2 outbursts that were after perihelion. And one of those was actually imaged by Andrea Aletti, who's one of the contributors to 29p. And you can see this is after perihelion. So here we are. We know it's a very spherical nucleus. Like if part of the nucleus had a darker or a lighter spot on it, you would have seen a variation as it rotated. So not as only is it very spherical, it's evenly distributed, the material over it. Okay. So here's my attempt at looking at the rotation period. And the idea here is that there's just one area of which is more active on the nucleus, and therefore the outbursts happen in a periodic fashion. So this is using all 16 outbursts and looking for patterns. You can actually see that the ones that were during the run-in towards perihelion, they could be explained as outbursts happening one revolution later or two revolutions if you assume there's a rotation period of about 15 days. And it's pretty convincing that there's something going on there. Right. How are we doing for time? Oh. Okay. Right. Has anybody heard of the Devil Comet? The Devil Comet. Well, 12P Pons Brooks is a Devil Comet. Our first Comet Chaser's image on that first outburst produced a reaction in the social media that because it looked like this, it not only looked as though it had two horns on it, it also looked to be a very diffuse copy of the Millennium Falcon, a fictional spaceship from Star Wars. Quite a few people picked up on that. So this was very much in the States, I think. And you can see why. But why really did it happen? Why did it do that? And it's all to do with it being a spherical shape. I think I predicted that. I said it's a sphere to be able to produce that. And this is now where I go back to my physical chemistry. So here's why. What I'm just going to show you is the appearance of the object after each of those large outbursts. So not only did that first image show the devil's horns, there were 3 other times in a strong outburst it appeared in a similar way. And again, there's this 15-day periodicity between them. So what's actually happening here? Why is it doing that? So you can see there's a sort of symmetry, a line that you can draw through the nucleus of the comet so that the coma looks the same on both sides. Now, I've done that for all of those images. I've also added another one that Nick took of another outburst later on, down here. And what you can see is that the source of the vent that's ejected this material is opposite. It's on the nucleus side, opposite. So if you imagine it's there, it actually, from those lines, was only within, say, a 60-degree angle of the nucleus. It's in a restricted area. And that, therefore, explains why we can get a periodicity, because it's localized. The outbursts are localized. You know, this is an explanation of why that period is likely to be the true one. Now, remember I was saying about you get this dust cloud and the gas inflating it. Well, depending on the intensity of the outbursts, you might not have enough gas. And in the case of 29P, the nucleus is so big that many of the outbursts can't actually expand and accelerate the dust beyond the size of the nucleus. And so you get, we call it the Pac-Man appearance of the outburst coma. But in the case of 12P, and these are very intense, these are the intensities expressed in terms of the extra light that's being reflected from the dust cloud compared to the light reflected from the nucleus alone. So you're getting 1,500 times more light being reflected back to the observer in the most intense case. So if we look at outburst 8 in a little bit closer, that's down here, you can see the patterns there. And what happens in practice is that the gas is expanding and the pressure is dropping all the time. And what you won't quite realize is that gases are made of molecules, and the molecules have spaces between them. And although at 1 atmosphere pressure they behave the way we know it, wind and so on, that dynamic impact on the dust cloud continues as the pressure decreases. And there's a sort of period whereby the inflation can accelerate the dust, and the dust eventually gets to a certain maximum speed, and then the pressure drops. So we talk about the behavior of the molecules, the gas molecules, in terms of what's called the mean free path. That's the distance it travels before it hits another gas molecule. So if your mean free path is bigger than the dust it's trying to hit, it misses the dust. And it's called the Knudsen region in the pressure range. And it's where this impulse from the moving gas actually eventually ceases. And you have a locked-in shape of the gas cloud that's expanding. Now, the thing about 12P is there's enough gas and dust that the expansion is accelerated beyond the size of the nucleus. And therefore, it's able to dynamically it's like the Venturi effect, sweep around the sides of the circular nucleus. And it leaves like a hollow cylinder in its wake as the expanding cloud goes up. Now, as part of my PhD thesis, I actually measured the forces of gas on a small object, right? And I'll show you 2 of the figures from my PhD thesis next. One is the apparatus I used to do the measurement, and the other is the result. So on the left is the kit, which it's like a beam balance, but it's an electronic one. And you hang 2 silica threads, very tiny silica threads from it, and it's in a sealed glass envelope. And the idea here is we're studying an object hanging from the microbalance that can measure fractions of a microgram changes in, and we do this at different pressures. So the thing on the right shows a plot with decreasing pressure, and it's actually the very same forces. This intermediate region here, it's from about 1/10,000th of an atmosphere to about 1/1,000,000th of an atmosphere pressure, is where the traction that the gas is getting, it's hitting the silica thread, the suspension thread. It's actually because of the temperature difference between the outside and the inside. And these are the different temperatures, 140 centigrade. And you see, you eventually get, once a Knudsen number, that's just where the mean free path is more than 10 times the size of the object, you lose the ability to impact on the particle. And so all of that, we go back to what I was showing you. The actual, because we know that this was moving at 300 meters a second terminal velocity, and that one over there at the start was 200 odd meters per second, we know that this active process only lasted just less than 10 minutes. It lasted longer than this one than that one. And the ratio of the size of that hollow cylinder that the sphere has embedded in as a sort of memory effect, that ratio to the size of the cloud is the size of the dust cloud where the gas pressure reached the point where it no longer was accelerated. So we actually have the ability to calculate the amount of gas that's in there, because we do know what the particle behavior is. And generally speaking, an average 2 micron sized particle is what a coma dust cloud is. And from that, we can get an independent measure of the actual amount of gas. Now, there's a paper come out that actually is quoting the mass of dust that's been released. So from that, we should look at the dust to gas ratio. And one argument is that these outbursting comets have an awful lot of gas in a cryomagma, and they're trying to get rid of it. So there we go, that's 12p. And so the final bit is just 29p. We've actually done 11 what are called apparitions since 2014. We typically get sort of 800 observations a year. This year we're doing even better. But here's a nice image that was taken by Charles Chambeau. It's a stack of 45 frames of 1 second exposures, right? I said, use a 10-second exposure. You know, you'll be fine. But because they were using an 8.4 meter telescope, the Gemini telescope, they backed off. They got frightened, and they only used 1 second exposures in 3 different filters. But they got a really nice color photo. So I'm not going to show you any of all the past years that we've done on 29B. I'll just show you what's been happening this year. And in fact, this one is the last month, what it's been doing. So it's actually, although this is sort of the quiescence period, before 2014, nobody had ever seen a mini outburst of this. And they're happening all the time, really, when it's quiet. And here you can see a number, and you see the advantage of lots of observers. So the next one shows that part of the light curve for this year, circled in red, but with the rest of it. So there again, you can see those small mini outbursts. And this plot is Julian date this way, and this is the magnitude. So that's a log scale. So, you know, you're looking at several hundred times brighter there, but down here it's only a factor of 2 or 3 times brighter. Now, there's just a few points I'd like to draw your attention to. Remember I said about the triggered outbursts, and that we may have had one with 12p. Well, we can get them all the time with 29p, and they only happen when we get a strong outburst, right? So, that image was taken because I alerted to the professionals of the fact there'd been 4 outbursts in a matter of just over 2 days, and that was in 2021. So 2021, there's a prime example, and that was the most intense that's been ever observed. And so they got large telescopes onto it. They also got the Hubble, and I'm a co-author of a paper that is being written from the Hubble data and Swift data. Right, and I'm a co-author. I've provided a lot of our numbers from mission 29p. But, and here's the problem, right? Remember I said they can't really get their mind around what's happening in a scientific sense to explain it. So the paper that will come out, hopefully, is explaining the outbursts that Hubble followed up on. Not in terms of an event where you get a crust opening up and lasting a matter of a few minutes, but they are actually, and this paper, if it comes out, they talk about a pit gradually throwing out 200 kilograms a second of material for several hours. So all our results on the rise from quiescence up to maximum have never been published in the community. And we've got, for 29p, we've got 10 events where we follow weak events, and they all show, just like 12p, this same behavior. And it means that the cryo eruption only lasts a few minutes, and everything else it then evolves from that. 1 minute. So in 14 years, we've actually covered and seen 255 outbursts in total. And I've just plotted them there to show the amplitude that you get in magnitudes and what the intensity is in terms of the amount of material that's been thrown out. Now, notice over on the top left, those are the triggered outbursts. And effectively, 29p seems to have two types of outbursts. So you can almost blank off the middle and say there's a mini outburst region and there's the strong outbursts. Now, if you plot this data against time and the intensity, this is what the cloud of data looks like. And in blue are the strong outbursts, and in red are the mini. Now, I just highlight those three regions of the strong outbursts, and you see that more recently we've had many more than a few years ago. Now, the orbital period of 15 years means this is about half an orbit of the sun covered. Now, if you look at the mini outbursts, take three equal, look at the difference between the seasonal differences there. And again, this is evidence that this is a different phenomenon. I haven't got time to, but one simple explanation is that these here don't have any gas dissolved in the cryomagma, whereas these here, like volcanic eruptions in the Earth, often have water dissolved in the molten lava. So there we go. And where does 12p look like on that plot? So I've plotted the ones we've got the measurements of the intensity, and you see there's 3 mini outbursts and 6 strong outbursts. So that these two objects, although they occupy very different orbits and seem to have a different origin, they actually share many, many things in common. So that's where I like. Oh, no, it doesn't show. Oh, that's interesting. It's one of the frame. Right. So I'll finish at that point and open it for any questions if there's time.
Richard, thank you very much. Don't run away. Stay in front of the microphones. You did very well.
Thank you.
You know, very scary on time. So,
I am on time. Yeah.
you're on time. Yes.
Oh, right. I've still got 6 minutes.
Yeah, but you started early.
No, but that doesn't count. I have
Oh, I know.
1845 is when I was going to finish.
No.
But I thought I'd
We will
have some audience participation.
We will have a short break in between to let people use the facility
Okay.
as well. Yeah. Questions from the floor, Nick, and then Jeremy, and then.
So, Richard, it's really good work, and the work you've done on 29p is great. One thing that I don't quite follow though, so your photometry, you're claiming that 12p and 29p are pretty much spherical.
Well, certainly 12p.
Every comet nucleus that we have actually got images of, they're very, very far from spherical. And what mechanism do you think would actually cause a comet nucleus to become spherical? It hasn't got enough gravity to do it. So why would that happen?
So the asteroid series is very spherical, and we know why that is.
Yeah, because it's big. It's got enough gravity
yeah.
to pull itself into a spherical
It's
shape.
because it's got a lot of water ice beneath it. And so it's called hydrostatic. There's a hydrostatic process that tends to, if you produce cryomagma, and if the cryomagma extends sufficiently around the object, this is where you've got to have, faith in the science.
I've got faith in gravity. and there's not enough gravity in a comet nucleus.
Well, these are big. Actually, 29p is 60 kilometers. It's got 100 times sort of, the
12p is
escape
maybe
velocity.
30, how is 15, 20?
These things have been existing for a long time, and the processes they evolve. The actual outbursts slow the rotation. There's a retro effect because the outburst happens on the morning terminator, near the morning terminator, and that has the effect of slowing the rotation rate. And so what happens over many centuries is that the whole of the surface, and remember that the surface is even. That's one of the findings of the work. That has been. It's a lowest energy, and this is thermodynamics. It's the second law of thermodynamics says, if you treat it as a closed system, then it would tend over time because it will rearrange itself, and the gravity will be the dominant feature.
Well, it hasn't done many other of the comets we've flown past. I think we're just going to have to disagree on this.
I'm going to stop this one because you've had your time. You don't have another half hour. Jeremy has a question. You've 1 minute to answer.
You talked about the molecules that being asked about. Is that just water? Are you talking about other molecules in the mix?
Okay.
And what is the source? Is it multiple sources? Do you think it would?
So we know the carbon monoxide is definitely the source in 29P, and it's the most effective. But things like nitrogen, oxygen, carbon monoxide, they're all chemically similar affinity. I've not talked about chemistry here, but there's a paper that you can read about the fact that you can transfer energy into the inside of the comet by a process of enthalpy. So you convert the ice into the sunlight heat converts the ice into a gas, and the gas during the night side goes further and further into the nucleus, and it does its processing there. So you get a differentiation within the nucleus, and that's what the professors find it difficult to say. Anyway.
Thank you. One last question here.
It's interesting you mentioned Halley right at the beginning. So, I mean, that's very far away. Is it at all possible to image that? Would I need something like Gemini North or Hubble or something to see that?
It's currently magnitude 25.
Sorry?
It's magnitude 25.
Magnitude 25.
Does your telescope go to that? Yeah. Halley, by the way, has a rotation rate of around about 7 days, so it fits this slow rotation period for factored dampers.
And it's shaped like a peanut.
Yeah.
No, Halley has an oblateness of 0.5, so it's one axis is half the size of the other. So it's not a classic, the 12P and 29P have been able to evolve into that shape over a very long period. And the amorphous thing, actually, amorphous because it forms in what's called a stochastic process, it's a random process, right? The way it then, if it stays pristine, when it then starts to do things because it gets near the sun, the evolution should also reflect that stochastic nature of the process, and you shouldn't be able to get an outburst that builds up and then slow down again. So in the case of 29P, if it was amorphous, it would be eroded gradually more and more, and its shape would go further and further from a sphere, and 12P as well. That's what amorphous ice would predict. Surface erosion over, and you would have to go to a more irregular. It has to go to.
The problem is postulating that they're spherical based on the observations.
Oh.
And I think that's a fairly big step.
No, it's not. It's not at all. It's actually definitive. There's no, if you're an asteroid observer,
We can discuss that.
it can't be anything but that.
Oh, that is the thing that anyone that goes over time or whose phone rings has to buy around. One last quick question for Paul.
Paul,
Yes, your equation for the mean free path, can you just put that up a second?
I can't. Yeah, have I put it on there?
It's not on there, it's on 3 slides black.
Oh yeah,
The
it's.
dimensions of that are very strange.
Yeah, I just put it's proportional. I haven't put the full equation. I've just said it's proportional to those quantities.
Sure, it was an equal sign, Richard, not proportional.
It should be a proportional sign.
Oh, okay,
Yeah,
right.
it's not an equal sign.
No, so it's
it
not
should be
dimensionally correct.
No, it's not. No, it's various other parameters in the
Right,
equation.
okay.
Yeah. Oh, yeah.
How different are these comets and asteroids from an object like the Oumuamua?
Oh yeah. How different?
I don't say the question again.
So how different are comets and asteroids compared to the object called Oumuamua, which was an interstellar object that passed through our solar system? Then they're not really. There were 2 interstellar objects. One appeared just like a comet, but Oumuamua, I'm afraid, we've got to wait for more observations and find another object. Like
in terms of its shape, if it's 10 times longer than it is wide, how does it compare with other objects in the solar system?
Yeah, that's not been borne out. That was something that came up initially. Alan Fitzsimmons, I think the shape is more like 4 or 5 to 1. in reality. It's just the data was misread.
And is it true that all the objects in the solar system are less than 3 to 1, all the other objects?
It's not far off, yeah, not far off. And also all the asteroids with rotation periods greater than 5 days is number 5 or 6%. So we have about 3% of comets that do this sort of thing. So again, that sort of fits in with this slow rotation thing. There we go.
Richard, thank you very much. And let's do You are the chair's nightmare, you know that. Thank you, that's really interesting. Enjoy your phone as well. Okay. Right, we just have a quick couple of minutes while our next speaker sets up if anyone wants to quickly use the bathroom or something. Now's the time.
I'll put my power on as well.
I'm going to introduce you, Mark.
Power? I see no power. Give me one, if I can plug one in. That's
Can I just ask we all
You go.
turn our phones off,
That one's yours.
watches off,
Junk. You've done.
Yeah, I'm just trying to retrieve my.
Some water. Yeah. You can introduce them.
Are you good? Did you want to?
Let's get going.
Right. Are we all sitting comfortably? Yeah. Phones off? Watches off? There is a fine, I have to tell you that. Yeah. All right. Ladies and gentlemen, it gives me great pleasure to introduce to you Mark Hardacre, who has recently taken over after the sad demise of Bob Misen, the chairmanship, you called it chair?
The chair.
The chair
Yes.
of the Commission for Dark Skies. And so I invited him along to his first meeting at council this afternoon, but also I wanted him to have a chance to talk to you and to those on YouTube about where we're at with the commission, his plans and so on for what he's going to do. Mark's been an amateur astronomer since he was the mighty age of 8, and he joined the BAA in 1968. So, I mean, obviously most of us weren't even born then, were we?
I wasn't either.
He's had a career in sales, marketing, and also fundraising. And like many of us then, when time became his own again, he returned to astronomy. And he's deeply involved, is deputy editor of the magazine for SPA, Popular Astronomy. He's treasurer of his local club, Fordingbridge Astro Club, board member of the AA VSO, and he is the CEO of Mark Hardacre Astronomy.
I would be, wouldn't I?
You would be.
Nobody else
Who
could do
else
it.
is going to do that? So, Mark, the floor is yours to tell us all about where we're going with the commission, what's been happening. I know it's been a difficult time, and big shoes to fill, haven't you? So
Indeed.
I'll leave it up to you.
Thank you.
Thank you.
Good afternoon, good evening, ladies and well, it's nearly morning actually now that Richard's finished. But he was meant to give me a plug as well. We forgot to do that. So it is my a real honour and a privilege to address you, the BAA, today. As Janice said, I joined when I was 10 and 2 months. There was a slight period where then I was not a member, which was most of my working life, to be fair. I lived 29 years outside of the UK, came back in 2018, and life began again properly. Out came the telescope. I'd been a passive astronomer for many years, but I became very active again. Very active within my own club, within Fordingbridge Astronomers. Many of you will know Steve Tonkin, who is one of my very close friends. He's recovering from a serious car accident. Many of you may know that, or some may not. So he's just out of hospital in the last few days. So best wishes to him. Steve was one of the guys that pushed me in the direction of the CFDS, the Commission, or the Campaign for Dark Skies. The other one was Bob Misen, who I knew fairly well. He was at Wessex, which is just down the road from where I live. I live in the village or town now of Verwood in Dorset. I'm not originally from there. You can tell by my accent. So if you press the red buttons, you'll get the subtitles of what a Yorkshireman is actually saying. I never dreamed I would be standing in front of the BAA today. And I never dreamed I would be in a council meeting. It was something that I've always dreamt about. So this is a proud, proud moment for me today. If I can go on, this young gentleman here on the top left, our friend Bob Misen, I think many of you know him. It was a sad day when we lost him. And the commission really struggled a great deal after his departure. The reason really was that he was a one-man band in many ways. He was a bundle of activity. Many of you met him, will have seen he was an absolute bundle of activity, up and down the motorway, presenting here, planetarium there, doing all the things that he did. And to replace the chair with one man really isn't possible. And that prompted us really that we have to make some changes, or that we needed to. Howard Lawrence here in the audience took over as chair and withstood the pressure, let's say, for 2 years doing that. And that was tough work. So we have to thank him for a lot of what he did. And the loss of Bob, not only Bob, but people like Graham Bryant and other pioneers, really caused a major disruption, a dislocation of the work that was being done. But, in some ways, dislocation and need for change is a good thing. And we regret, of course, Bob's passing, but maybe that's a time for us now to change direction, change about the way we're thinking about dark skies and how it affects us in astronomy. So last November, Howard and I and a
couple of the committee were talking about how do we continue, and I said, well, what does it say? What did the last AGM? What did we do in the last AGM? And Howard said, what AGM? Well, I mean, didn't the last secretary record what happened? What secretary? Well, surely there's some notes. What notes? So we decided it would be a good idea to call an AGM as if it was our first one, and that's what we did. And happy to say that since November of 2024 last year, we now are properly formed. I'll come on to that in a bit. But we really did then resolve, as it says there, to dust ourselves down, shake off the bad memories of what happened with Bob, and press on. So what we're doing really is in memory of Bob and all those that preceded him that have done a terrific job for us. We have some challenges, and these are some of them. As it says here, the shift from astronomy-based dark skies advocacy to a more persuasive argument for health. We are too small, and we are too fragmented, and we are too niche to have the impact that we need to get dark skies. I think we all in our astronomy clubs and our work that we do, we all know how important it is, but how do astronomers influence people that can change things? Very hard, very hard. So we have to think about how we're going to do that. There's a need for a cross-disciplinary campaign. Not only do we in the campaign have to stick together, we've got to bring in all the other astronomy campaigners, of which there are several. We know of Dark Sky Partnership, DSI UK, and so on, and there are more. And we need to bring those together so that astronomy is speaking with one word, with one voice. To that, then, we have to add others, a coalition of the willing, let's call it, people from health, wildlife, and so on, that are going to get this job done for us. The other thing is, we have, I don't know how many, we've got 2,500 members of the BAA, I believe. How many astronomers do we have in the UK? How many amateur astronomers do we have? 20,000? 50,000? I don't know. But every one of those has got the same problem with dark skies. How do we find a way to motivate all those amateur astronomers, not just BAA members? How do we motivate them to help us every time they go out at night and when they talk to people? Also, the nature of astronomy has changed. We just had a talk out here talking about smart telescopes. That's completely changed the way astronomy has been done. It's not so much visual anymore. There's a lot more. I just leave it outside. I'll go in the living room and blaze away with my sea star. It's true. I mean, I'm sure a lot of us in the room do that. I do. When it's you've got an hour clear, out with a sea star, nice images. Boom. That's not astronomy, say some people. But so that's the nature of the beast. It's changing. Another challenge: how do we tackle the satellite constellations? Is it our job? Do we have the power to influence that fella over in the States who will remain nameless? He's got even more powerful, hasn't he, in the last few months? And what about SQM monitoring? What about actually measuring the brightness, the level of photons coming down from the sky? Is that something that we can do? Do we have the resources to do it within our clubs, within our organization, within the BAA? And what's its value? So all these things are some of the challenges. Not only that, we have that challenge. And I'm sure everybody in this room has had the problem. We've had a most dreadful 2 years of weather. And I can't remember a time like that when we've just almost forgotten how to go out and do observing because it's been so bad for weeks and weeks. Mr. Walt Disney said, the way to get started is to quit talking and actually begin doing something. So that's what we really wanted to do. That's what we started off with our AGM. We gathered in a room in town here in London, and we called our first AGM. We appointed a chair, and a treasurer and a secretary. So we've put the campaign, the Commission for Dark Skies on a decent footing now. We've established a committee. We have looked at our financial position. We have some funds that we can use to drive the program along. We've drafted a new constitution. Constitutions are admin and they don't do anything. But when you've got one, it really focuses on what the things you should be doing and some of the things you should not. We've drafted and published now our aims and objectives, and we've started looking at our key objectives, key activities, and what we're going to do. Those are the guys that have put their thingy on the block. That's me, clearly, and Howard, you know, who's very graciously offered to stay as deputy chair and help me out. I am not as detailed. I don't have the, that's wrong. I am not as knowledgeable and wise as Howard or Steve Tonkin or many others, Dan Oakley and several, in the field of dark skies. I rely on others to help me, and that's going to be what Howard will do and many others. I look forward to working with them all. But we have a secretary now. Kevin Attry has decided to, willing to help us, and a treasurer, so life will proceed. And we then have a committee of these people. Some of them you may know. One of them is in the audience this evening, Richard, who has been with us right from the beginning. Those 13 people are the heart of the organization, but what we really want to do now is expand into the body of observing of our amateurs within the UK and outside to get something done. And that's a challenge that we're going to be facing very soon. As I said before, having a constitution, having a piece of paper doesn't get anything done. It tells us what we want to do and why we're going to do it, but really it needs to be translated like this into our aims and objectives. And this is what we decided was the 6 main things that we could really focus on. Obviously, reducing light pollution, reduction in an artificial light in outdoor spaces to minimize pollution's impact on us, on culture, health, wildlife, ecosystems, as well as dark skies for astronomers. You know, although that's where we come from, that's our DNA, we have to, in general, look at the impact of light pollution on human beings and animals. To do that, we're going to have to promote awareness. We're going to have to drive awareness everywhere about not just astronomy, that's easy, but wildlife, human well-being, and the importance to us of our mental health of dark skies. Promoting that awareness is going to take some oomph. You know, we've got to get social media, we've got to get into the press, we've got to get on the TV, we've got to get in front of MPs and other local government representatives. And that, again, is going to take a group of people within our BAA organization, within our local astronomical societies locally, who are allied with us to push us forward. We need to encourage responsible lighting practices with the industry. The lighting industry is aware of our quandary and our issues. We need to work with them to promote the use of outdoor lighting that minimizes glare, that doesn't blast up into the night sky, that is the right color. And that, again, that's going to take connection with the industry, persuading and cajoling. In many cases, we're pushing against an open door, but in other cases, we're not. You know, people, there's a reason that headlights are blue-white on cars, which we all hate. The yellow ones before were perfect with 2,700K temperatures were perfectly okay, but now we've gone up to LEDs. Why? Because they're cheaper. Huh? We need to engage with communities, as we said before. dark sky initiatives, encouraging grassroots activity at local societies, local clubs, schools, cubs, flashing up the light. Oh, that's bad. Turning off the light, making sure that people are aware of what's going on. As I said, number 5, collaboration with our friends in the environmental movement. They have a much bigger bang than we have. Your kids and grandchildren, they will talk about what's happening with animals and bats and birds, and are more aware of it. They're aware of our carbon footprint much more than we are at our age group. I look around the audience. And we need to be hooking into them. We need to be communicating with them in the way that they communicate with us. And we need to then look, last one, for policy change. That's going to take some real energy. We have to get in front of the APPG, which is the all-party parliamentary group for dark skies, a group of MPs and Lords who are pushing this in Parliament. Those are the things that we have to do. What we've already started to do is improve the way that we look, the way that we are visible to the outside world. Most importantly, we have changed this last week. Callum is hopefully on Zoom. Callum, thank you very much. He's done a great job and ported all our old websites into the BAA website this week. So we now look like a BAA section. And I think that's important. We were standalone because, well, Bob was standalone. We know Bob was I think it's important that we are part of the BAA. We are much better together than we are separately. So we've brought in the website into the main BAA website. It needs to be updated. So once it's ported across, now we need to edit it, and we've got people that are willing to do that. We think by June we should have a BAA-looking website for dark skies, and that will help. And of course, the website is just part of it. Social media is the other thing. I know, because I've already heard it once today, oh, don't talk to me about social media, Madam President. But that's the way our kids think, right? All of them. They wouldn't be listening to me here. They'd be all tapping away on their Instagram, taking pictures of me, uploading it, because that's the way the world works. We have to think that way. We've got to start working that way, and it's tough. Facebook, probably some of us do Facebook, because that's what older people do. Instagram, that's me. I'm 67 years of age, so I've got no room to talk. But Instagram, LinkedIn, all these things, this is where we need to be and need to be communicating at that level. We have appointed a social media champion. Her surname is Misen. So Bob's daughter has offered to help us out and keep our social media face up to date. And it's nice, isn't it, that Bob's daughter is going to come and help us. So I'm very, very proud of that, very pleased. We have a Facebook page. This is our Facebook page, I believe. If you are a Facebook user, please come and join us. We have around 1.2 thousand followers. Find us on there. We're under the Commission for Dark Skies Protect the Night. And put something on there, message us, and we'll know that you've listened to what I've had to say. Key activities, next one. The APPG is under new leadership since the election. So it's been revamped. There are new faces. Some old faces have left. It's co-chaired by the Astronomer Royal. So Martin Rees is the co-chair, together with, I think, James Wilde is the current co-chair. It was Andrew Griffith, but I think Andrew has stepped down. I do believe, however, is that correct? Nevertheless, never mind the parties, this is a cross-party activity. The APPG is working very well with the RAS right now, and I think it's time for us also to become more involved, muscle our way in a bit, and to start to lobby our MPs. Again, all of us in this room have an MP. I have talked to mine, Simon Hoare, specifically. I've said to him, you are the MP for a region that has a dark sky site in it. Cranbourne Chase International Dark Sky Reserve is on your patch. So you need to be on here, Simon. And he's agreed to look at that for me. And I think if wherever you are, even if you're in a city, you know, sir, Mr. MP, have a look. You see, you can't see the stars. Why don't you just come and join us and see if you can help? And you know, that lobbying, pushing will get activity, will make them aware at least of what we're talking about. And I think also that would be a good thing. It would help us to gain a bit more visibility for the BAA and the CFDS, of course, at government level, because that's where things get done. You know, we can go around one by one changing lights in our village, in our street. That's good. But to get things done on a national basis is going to take a bit more horsepower. The other way that we have, and this came really to the top of the list, this slide should be number 1 or number 2 at least, and that is to participate in a coalition of the like-minded, is what we're calling it. You may have heard this being spoken about before. We don't have the clout as astronomers to get things moving. We're seen as a clique. We come out at night. It's true, isn't it? You think of it. We look like Patrick. Everybody, you're an astrologer. No. Oh, can I have a look? Is that the rings of Saturn? Yeah. And we love the public. I love doing the outreach. I'm sure you all do too. But those same people will watch Countryside, the Countryside programs on TV. They'll sit and listen to Chris Packham talking endlessly about preserving this or that. They've got the clout to make things happen. And I think with the APPG and us working together with the environmental people like Bug Life, people like the Butterfly Conservancy, which I'm also a member of, bats, bees, nature, wildlife trusts in general, they have a major impact on our young people especially. We're working right now with the CPRE, the Campaign for the Protection of Rural England, as well as the lighting industry, to try and put together a coalition that speaks with one voice, rather than this, you know, little voices in the dark and in the light, trying to pull this together as one voice, one campaign. That's going to be tough, and it will not succeed tomorrow afternoon, but we're going to start. We're also going to try and re-establish what, this is down to tactics now rather than strategy. We're going to try and re-establish one of the things that Bob was very successful with, and that was the CFDS newsletter, which went out on a monthly or bi-monthly basis, or quarterly, Howard? Quarterly. So that went out to around 1,000 people, we think, and it was traditional. It was printed out and sent out. Latterly was more PDFs. And we need to do that. We need to get that started again in a modern way, in an electronic way, of course. And we also need to build within each astronomy club in the UK, of which there are, how many do we know? I think around 200, 300 clubs. Yep, that's a lot of, so if we had one representative within each club, and I'm going to work with the FAS to help us there, as well as BAA, of course, but if we can get one representative within each club to be our eyes and ears on the ground in that area, to be the recipient of the newsletter for distribution to their people, or discussion at their meetings, as well as the eyes and ears for feedback to us, I think that would be very, very useful. I'm looking for an editor to put that together. It's going to be a couple of pages. I'll start it off. Maybe Howard, if he for a month or two, might help me out, but I'm looking for someone to do that. And we're going to try and get that started again by the end of May, so that we get some more activity. We're also, I mean, it's trying to contact national highways. Have you got any potholes around your way? Trying to contact national highways or charities or get on BBC News is a big task. You know, you've got to have a good story, well rehearsed, presented strongly, with one voice. And that's what we need to do when we talk with what I call here relevant media and institutes. This is a story that came from the BBC website. I can't remember what date it was, but it's only a couple of days or weeks ago. This didn't come from us. It should have. This should have come from us. We should have been in touch with the BBC and said we're going to change this. Instead, Dorset Council has been approached by others. We need to be part of that story, that we're at least included in this story. We were not. We were not even mentioned. This was all about health, mental health, birds, butterflies, no word about astronomy. And costs, you know, remove the expensive lights, replace them with cheaper lights. Government, council, love it. So let's get up and find a way in. Local press, national press, and broadcasting, we really need to get in there. We've also talked about getting data. Government likes data. How many votes will you give me? I'll give you 50. How many? No. How bright is the sky? Well, it's 24 million. They want data. Okay. So one way we could possibly get data is looking at measuring SQM measurements of the sky's brightness, where we are, building up a map. You know, there's already, we can get maps of dark sky, but it would be useful to have a timeline, so that map evolving over time that says, look how the town of Verwood in Dorset, you know those 300 houses you added up the lane there? Look how that patch of light has grown, and it's removed another, that's connected with another one in Shrewsbury. And here we got, and slowly we're eroding away the light, the dark areas we have. And it's very important in campaigning, I'm sure all of you know, is to use facts and not hearsay. And I think this is the way it should be. And I think that, no, facts, this is what's happened over a period of time. So those are some of the real key activities that we're working on. We need a lot of help. We need help of you, the members, of you and your astronomical societies, the FAS, and all the other people I've talked about here to make this happen. We've been busy. We haven't been as busy as we thought we were going to be. We're still trying to get issues with the bank sorted out, but I just wanted to give you, we've been busy with meetings. I'm not going to go through these individually, but outreach is something we love to do, getting out there and doing things, breakfast presentations, and lobbying. We've already started contacting our MPs and so on. So in summary, because you'll be pleased to hear I'm done, we believe that this Commission for Dark Skies needs to become more visible and more active. We think it's an important part of the BAA. We don't want to be separate, we want to be part of this organisation. And most importantly, we think it's important to join in a coalition of the willing, bringing our multiple astronomy voices together with much louder and powerful environmental organisations to get this issue even louder shouting to the public and get some results to reduce the pollution that is destroying our dark skies. I thank you very much indeed. It's been a pleasure to be here today.
Thank you very much, Mark. Perfectly on time, what can I say? Have we time for some questions for you? Yes. Have I any questions from the floor? Adam.
I'm not sure if you've addressed one of the main reasons, or possibly one of the main reasons for light pollution, which is public safety and security.
Yeah.
And you're also talking to local authorities, and we all know they're actually bust. They haven't got a penny to even do what they're supposed to do. So to get them to do something different is probably, well, I'm going to say a possible difficult task.
Can I just repeat the question?
Yes, the question was with local authorities effectively bankrupt, how do we get them to change things, and also the aspect of public safety. You know, if you're going to turn the lights down, or our little old lady's going to walk around in the dark. First thing on they're not prepared to do anything. I'm also a local councillor for Burwood Council, and what local councils need and county councils above them is wherever possible to save money. So there is an opportunity, if presented right, to cut down your electricity costs, your maintenance costs by reducing the lights that's available, turn them off. You don't need them blazing away on all the roads. That's also happened in our town so far. What about the main roads? Do they need to really be on all through the night? And do they need to be so high? Can't we reduce the height? So yes, and these things, you're quite right, will take an initial blip of capital to change, which is not available. But the longer term, the P&L part of it, the cost saving to the council is apparent. There are, of course, questions about do we have to turn their lights off so that people can't see where they're going? No, it just doesn't need to be pointing up in the sky. They're not walking up there. We need to have the lights directed to where the people are walking, and not shining around the rest of the path. And I think that's a good argument. You know, can we direct the light down? Do we need the intensity, and do we need the 5K? Can we not have the 27K to 0.7K that we had before?
Are we getting any questions on YouTube or no? No. I'd like to ask you a question myself. I can take advantage of my chair position. You mentioned a lot of the other environmental agencies, but not RSPB or Woodland Trust, both huge organisations in the UK and both amazing amount of power.
Yeah.
RSPB particularly has a broader age group
Yes.
than perhaps astronomers have. And as you've rightly mentioned, they're really 10 times more aware of the damage that we're doing.
I tried to put them all under wildlife trusts on that slide,
Okay.
but you're quite right. We need to look at which ones are most impacted, have the most interest in dark skies. The butterfly people, for instance, it's not a big deal for butterflies. They are generally interested in the well-being of nature, but butterflies as such not. Moths, yes, but there's no moth organisation in the UK. It's part of butterflies, right? So this is butterflies, and there's a little corner like that. It's a bit like the BAA and little comets, you know. Sorry.
Brave man.
He's bigger than me as well.
No, I must admit, though, a lot of the butterfly people are actually very moth orientated too, aren't they? And you know, they really get it. So, I mean, that's a positive. The other side, might slightly related to my previous existence, is that it's not a crime prevention thing. There's, you know, what very often happens is areas are so lit up that it makes it easier for people to commit crime because they see what they're doing and so on. In the dark, they're always scared that somebody might creep up on them, you know, that sort of thing. And that's certainly from the law enforcement world. That's always been
and we have to overcome that. That there are many challenges that we have, as you have tried to point out, and not all of them are easy. But I think we'll get there. Sir. Yeah, the question was, is there a way to remove the pollution, to remove the dust and muck in the air? I think that is something that is out of our bailiwick. We don't have that within our skills. What we can stop is the light that is shining onto those dust particles reflected back to us. We're always going to have dust in the atmosphere, and it's become worse as we've industrialized. The haze that we had the other night was a lovely, beautiful evening for seeing, but very hazy where I live. So to remove the pollution, massive governmental, uber governmental. Not that I'm aware of.
Is there technology available?
Is the technology available? Sorry, is the technology available to reduce that pollution? And I think the answer to that question is no. How different would it be from carbon capture? I mean, I think we're talking about two different things here. Carbon capture is about removing CO2 from the atmosphere. The technology is very, very new there. Is it a solution to our world global warming issues? Maybe. There is no equivalent. For light pollution, which is what we're talking about here, it's two different things. We're talking about light, too much of it, and that's where we can do something. The pollution aspect of it, the pollution that sits above Hong Kong or other major cities, that's the dust that we generate. That's what the light is reflected then off, lights up the whole sky. But I don't think we can touch that aspect. We don't have the manpower. Yes, yeah. Thank you.
Right. Well, I'm going to draw it to a close now because Nick is champing at the bit to get there. Can I just say thank you again? Don't step behind me. And round warm of applause. And welcome to the BAA.
Thank you very much.
Thank you.
Unfortunately, I have to leave. I have an appointment at 8, so I'm very sad. I would love to stay, but the next time I will be here, the 4th of June. I'm sorry.
That's okay. Can I just ask those of you who've brought cups, glasses, or anything into the auditorium, can you kindly take them out to the table while Nick is setting up, please? It's just, we're guests here. We're guests here of the IOP, so we don't want to abuse that looks as if it's important.
No, I don't need that bit.
We don't want to abuse the hospitality.
That's Mark's power supply.
Excuse me, I'm going to pull this plug out.
I seem to have been somewhat truncated. Yeah, they know who I am.
Sorry. In case you didn't know, it's what's your name?
Me.
Nick James. Something to do with comets.
It's not. It's Sky Notes.
No, you're something to do with.
Oh, I am. Yes.
Yeah.
I am.
Small. And he's going to deliver our Sky Notes. Thank you. Don't push me off.
I'm not.
Bad enough.
Thank you, Madam President, for that wonderful introduction. Don't stare at me like that. You put me off. Simon, could you put the lights down a tad, please? So, if possible. Anyway, okay, Sky Notes. So we'll start. So we had a lunar eclipse recently, early in the morning. I got up early to see it from Essex, and it was cloudy where I was, but a number of people were lucky enough to see it, and there's this nice picture here from Kent, which is actually the other side of the Thames from me, in that dodgy bit of south of the Thames, where obviously it was clear enough to get some pictures. Starting in the centre of the solar system, though, the sun's been quite active recently, but not at the moment. This is as it appeared this morning, or maybe yesterday evening. say 20, yeah, sort of fairly recently, not a lot on it. But in hydrogen alpha, there's been quite a lot of activity. This nice image from Anton Matthews showing a nice prominence. And we've got this one from Gary Eason as well, showing a lot of activity on the sun. So the sun's been active. Simon, could you turn the floodlights off? Because it's like I'm being interrogated here. Yeah, exactly. So the next shot's going to be a nice video of Northern Lights, which is going to be suffering from a lot of light pollution, unfortunately. This is an aurora that Dennis Brzezinski got on the 24th of March. So he's had a lot of auroral activity up there. Almost every night he's getting some aurorae, and that's his form of light pollution up in the north of Scotland. He doesn't get much in the way of other light pollution, but he's regularly getting aurorae to the north of him, which is distracting him from comet observations, which is not a good thing. The other form of light pollution we have, of course, natural light pollution, which I don't think we can do much about, is the moon. But at least it has the good grace to disappear every couple of weeks or so. Where are we at the moment? So we have new moon coming up on March the 29th, which is actually the day of the partial eclipse, which I'll talk a little bit about in a minute. And of course, full moon, which was back on March the 14th, was when we had the lunar eclipse. Nice picture here of the straight wall, taken by Bill Leatherbarrow. There we go. Which is a kind of really nice feature on the moon. You can see at particular lighting conditions when it's casting a shadow. And that crater is that Bert, that one? Yeah. So I've got a few pictures of the lunar eclipse. So just going through these. So Andrew Patterson from France, fairly early on in the eclipse as the umbra was moving across the moon. Then a couple here, one from Grant Privet, who was in Wiltshire, and one from Mazen Younis, who actually managed to get some images from Morocco. The lunar eclipse was a total lunar eclipse, but from the UK, the moon set pretty much at the start of totality. So we didn't actually get to see totality. This one is from Alan Dowdall in Newbury using a sea star. So the first sea star picture of my session today. I've got a few. Obviously working very well there, and clearer skies in Newbury. And then a little bit further on, Alan 2 up in Moray got a nice image as the umbra was almost covering the moon. So this was heading towards totality. You can see here very clearly that the shadow of the moon, the shadow of the Earth on the moon is much larger than the moon itself. So that's a good indication that the Earth is a large round object. So how flat Earth people explain lunar eclipses, I have absolutely no idea. I think they probably have more trouble with explaining day and night than lunar eclipses, but they seem to stick with it. Much further west than us, this is in Canada, or Northern America, as it might be soon. This is a picture from Nicholas Freeman, rather nice composite of the total eclipse, so going through the partial phases and then the total eclipse. We did have an interesting view of this total lunar eclipse, actually, which is, I think, relatively unique at the moment, and that is from one of the little landers that has recently landed on the moon. So you'll have noticed there's been lots of attempts to land landers on the moon recently. Some of them topple over, but this one actually succeeded in landing, the Blue Ghost, and it landed in Mare Crisium. And so towards the end of the total eclipse, as the sun reappeared from behind the Earth, this spacecraft got this picture. And this was widely distributed in the media, and it looks remarkably like a diamond ring at the end of a proper total solar eclipse. But of course it can't be, because the Earth is way, way too big The Earth is something like 3 or 4 times the diameter of the Sun here. So this is not the corona, the solar corona, around the limb of the Earth. What this is refracted sunlight. So sunlight refracted around the Earth's atmosphere. And the reason it's lumpy and blobby like that is because of clouds. So basically, depending on where clouds are around the atmosphere, you get bright and dark parts. But it's still an interesting picture. So this was, I think this is the only picture of that eclipse taken from a spacecraft landed on the moon. But it's not what it seems. It's still an impressive picture, though. So coming up Saturday morning, we have a partial eclipse. This is quite an unusual partial eclipse because it doesn't have an associated totality. The penumbra, so the shadow of the moon on the Earth, is actually passing over the pole, and the actual umbra misses the Earth. So it's quite unusual for me because normally if there's a total eclipse, I travel off to see the total eclipse. And so I very rarely am in the UK if there's a partial eclipse. But on this occasion, I will be. And I'm planning to live stream it from Chelmsford on Saturday morning. It'll be on the BAA YouTube channel. So just in case it's cloudy where you are and you want to see what it looks like from Essex, just tune into this same channel that the meeting's being streamed on. There's a paper in the Current Journal from Peter MacDonald, who does us all a great service producing detailed tables of the phenomena of these eclipses. And basically, the times are in that table below. So from London, from Edinburgh, it starts around 9 minutes past 10. And it finishes around 7 minutes past 12. I think from where I am, this simulation here is for Birmingham, which is kind of reasonably central. So again, starting about 10 a.m. and finishing about 12. The weather forecast for Saturday morning where I am looks quite good. Hopefully it will be where you are too, but it's a good opportunity to see quite a reasonable sized partial eclipse from home. So just quickly sort of running through the sky. So the days are definitely getting longer at this time of year. We're past the spring equinox. We're moving towards the long summer days and short summer nights. But at the moment, we still have about equal daylight. In the evening, it's kind of getting dark about 6:30, 7 o'clock, something like that. I think, when does the hour go back? Is it this coming Saturday? This Sunday. Okay, so we go to BST then, so that'll mean that the evenings will be lighter. Means I can get home from work and actually see the evening twilight. So at the moment, we've had both Venus and Mercury in the evening twilight, but both of those are gone now. There's a really nice picture here, again from Grant Privet, of Venus and Mercury above the horizon on March 12th. You'll have noticed that Venus, which has been hanging in the evening sky for a long, long time, very, very rapidly disappeared. And the reason for that is that it went through inferior conjunction, so it's at its closest point to us, so it moves very rapidly in the sky. It's actually quite an interesting inferior conjunction, which I think it was actually last Sunday was inferior conjunction. It's quite a long way north of the sun at inferior conjunction. So it was about 8.5 degrees north of the sun. What that means is that effectively Venus was visible both in the evening sky and the morning sky from our latitudes, which is quite an unusual thing. But a number of people managed to actually image Venus in the morning sky actually before inferior conjunction. Of course, it's coming up to inferior conjunction, which means that it's a crescent shape. And here's a nice video showing what Venus looks like in a telescope when it's relatively low down. How Paul manages to get those amazing drawings he does with the seeing like this, I don't know. I mean,
I made them during the day when the seeing is not.
well, but even during the day, I've tried taking images of Venus during the day, and the seeing is pretty hopeless.
Well,
so. It's probably Chelmsford has a particularly bad thing. But anyway, so it's been a really thick crescent. Unfortunately, on the day of inferior conjunction, when I was going to have a go at trying imaging it, it was cloudy all day on Sunday. But a very thin crescent, but very large. It's kind of like an arc minute in diameter, so a really large crescent. Some comparisons here. I rather like this one. This was posted on the observers pages. It's Mark Charon, and it's images of Venus and Mercury taken at the same focal length, giving a good idea of the relative sizes of those two planets. Both of them crescents, because they were both coming up to inferior conjunction, but Mercury obviously much smaller, a much smaller planet and much further away. Richard Seven's image here, rather nice, showing some extensions. So as we get a bit like we saw in that image from the moon of the sun behind the Earth, because the Earth's got a thick atmosphere, light gets refracted around that atmosphere, and the same thing happens with Venus. So near to inferior conjunction, the horns of the crescent actually move beyond 180 degrees as we get closer and closer to conjunction. And in fact, if the inferior conjunction, the elongation is small, we can sometimes see a complete ring of sunlight refracted around Venus's atmosphere. I don't have any pictures from this, but I did see one from Pete Lawrence, which actually showed really extended horns on the crescent. Of course, another thing that we can do now is actually image the surface of Venus. Now, this is something which 10 years ago would have been considered completely impossible for amateurs to do. But with appropriate infrared filters, when the crescent is small, so that it's possible to take long exposures without saturating the camera on the illuminated hemisphere, we can actually see infrared radiation from the surface, which comes up through which penetrates the clouds. So there's some transparency at infrared. And this is an example, I think, by Peter Tickner, showing features on the surface of Venus. So here they are. You've got the overexposed crescent, but you've actually got dark mottling on the surface of Venus, which actually matches the dark mottling that you can get when you use a simulation in WinGPOS to show you what you might expect to see. So it definitely is real. And in fact, there's possibility even that we have seen changes in the surface of Venus for things like volcanoes, volcanic activity. But it's a really interesting thing now that amateurs can do with modern cameras and modern filters. So going away from planets, I just wanted to show this picture because this is a really nice example of what you can do if you've got a nice remote telescope in Morocco. Mazen Yunus has been doing some fantastic work. He, a while ago, he wrote a paper in the journal about how he set up his remote telescope in Morocco. And it was a lot of hard work, but it's really paying off now in terms of the images he's managing to get. And this is one that he posted to the BAA Observers site. And I think one of the nicest images I've actually seen of this area around the Horsehead Nebula and the Flame Nebula in Orion. Really, really impressive imaging. So let's move around a little bit in the sky. As the sky gets darker, we've got 2 planets left out of that planetary parade, which you remember that the BBC went nuts over in February, when apparently it was possible to see 7 or 8 planets, 7 probably, I think, planets in the sky, except that you couldn't actually see some of them because they were in the twilight and some of them because they were too faint. Anyway, the 2 that are left now are Jupiter and Mars. Jupiter's still a really bright object, slowly going down in the western sky. So here is a typically extremely good picture of Jupiter taken by Martin Lewis with his big dob. Again, showing a huge amount of detail. And Bill Leatherbarrow is actually taking images of Jupiter. The moon must have been missing that night or something, was it? Hiding from from the permanently snow-covered peaks of Sheffield. So yeah, another good image of Jupiter. And of course, visual observers, Paul being sort of leading visual observer amongst them, also doing drawings of Jupiter showing all of the interesting features that the planet has. So the planet's still well presented. It is gradually disappearing down into the western sky, but it's a good object to observe, lots of interesting detail on its surface. Jupiter always is a fascinating object to observe. The other planet, well past its best now, is Mars. Much smaller, needing much better kind of optical performance to actually show stuff visually on its surface. I actually was lucky enough to use a big telescope after a talk I'd given to the Bretland Astronomical Society a couple of weeks ago. They've got a 20-inch telescope in their observatory. We looked at both Jupiter and Mars, and you could see detail on Mars's surface with it, but it's definitely, when you see images like this, it looks like it's kind of a fairly easy observation, but in fact, getting detail on Mars's surface at the moment is difficult. What's the diameter of Mars now, Paul? It's about 9 arc seconds. So it's getting really tiny, but it's definitely still another planet to observe in the evening sky. It's as well gradually disappearing into the western sky, but it'll be around for a while longer. Is that's the poles? Right. Okay. Thank you very much. From an expert in Mars, which is definitely what I'm not. Going around a little bit further, then sort of around 10 p.m. at the moment, we've got Leo and Cancer and Virgo. So we're getting into the sort of realm of galaxies. We also have Corona Borealis, which is a constellation which contains this mythical thing called T Corona Borealis, which I think is a big con by the variable star section, because it's supposed to be going into outburst anytime soon, but it hasn't yet. It will. Jeremy assures me it will. But just starting kind of some interesting stuff that's been put on the website recently. So this is in Hydra. This is an example of what amateurs can do with spectroscopy now. So this is Robin Leadbeater taking spectra of two distant faint galaxies, and they've both got very similar redshifts, but it's really impressive that an amateur spectroscopist can take images of these galaxies and actually deduce redshifts. So I was really impressed by this, and I think just the developments in spectroscopy, amateur spectroscopy, are just moving ahead very, very rapidly now, and Robin is usually kind of leading the field in this, in picking interesting objects to use his spectroscope on. So in that kind of region of sky as well, we have in Cancer this object called OJ287. I did actually Google OJ, and it came up with OJ Simpson when I did it. But it's actually an active galactic nucleus, about 4 billion light years away. Mark Kidger is doing a program with the VSS to observe it. It's had a very chaotic light curve, and Martin Mobley has been imaging this. It's actually in, I think, a fairly faint state at the moment, but an interesting object to observe, and currently well placed in the evening sky to go after if you're looking for an interesting subject to do some photometry on. Rather more regular is this. This is R. Leonis. This is definitely an object that's worth observing, much brighter, and it looks like it's kind of, it's just going through its bright phase at the moment, is it, Jeremy? Right, okay, and sort of on its declining branch now, but worth keeping an eye on. And I did mention it, but I thought I might as well put up the light curve. This is T Corona Borealis. Everyone's looking at this, everyone with a, well, I think, Steve Knight, how many images of this have you got with your sea star? 32,000 images. And none of them showing an outburst yet. But lots of people keeping an eye on this. We have lots of meteor cameras which will pick it up potentially when it goes off. We've got Steve with his sea star in the back garden doing it all the time. Lots of people keeping an eye on it. We all await with bated breath this thing going off. Whether it will happen before the next meeting, which is, we'll see. We'll see. Going around a bit further then, in the kind of morning sky now, we're getting into the constellations of summer. So Sagittarius, Scutum, Aquila, and Cygnus. But also we have this big sort of area. So you've got lots of Milky Way, and then you've got a Fucus and Libra, which are fairly barren areas, but there's some interesting stuff around in this part of the sky. And this I was rather impressed by. So this was done with a sea star as well. And what James Wakeman here has done is taken some images of two of the stars that we know of that have the highest proper motion, so Barnard's star and Wolf 359, and he's then compared them with catalogue positions and actually demonstrated quite nicely their proper motion. So I think, you know, the sea star and other smart telescopes are available, has really opened up loads of potential projects for people to do. And there's lots of our members who've been using them for all sorts of interesting stuff. So not just taking pretty pictures of things, but actually using them to image interesting parts of the sky. And I think this is a really good example of that, deciding that you're going to go and have a look at these high proper motion stars and getting some results, which are great. Okay, so going round to the dawn, Venus is now beginning to appear in the morning sky. So it will very quickly become a very prominent object in the morning sky if you're up early enough. So that's the kind of run through the night. I've just got a few things on interesting stuff that's been happening in the solar system nearby. So this is something that Richard wrote a really interesting news article on the website. This is a near-Earth asteroid called 2025 EF4, which made a good close approach to us. It was a reasonably bright object, and Grant here has managed to image it. So what you have here is a set of images with small gaps between the images, which he's stacked up with a few bigger gaps where he had satellite trails crossing across the image that he's not used in the stack. Peter Birtwistle got a nice light curve on this asteroid, showing that it has a rotation period of about 16 minutes and 10 minutes. So it's a kind of complex tumbling asteroid with two different rotation curves. Wayne Hawley, similarly. So if you're interested in this, have a look on the BAA website. There's a nice news article that goes into it, and another good example of how amateurs do some real science with relatively small telescopes. Meteors coming up. We have the April Lyrids, which are active between the 14th and 30th of April. They actually come to a peak on the 21st of April when the moon's about last quarter. So the moon will be kind of reasonably out of the way. It's low down. These meteors, because they're coming from Lyra, they're best seen in the morning sky. The radiant rises about 10:30 or so our time. So if you want to have a nice meteor watch, get up in the morning of April the 21st, April 22nd. And this is a set of images I got last year. There are quite a few of these April Lyrids around. They have a very variable ZHR, but it's definitely worth having a look. Right, I'm going to conclude with some pretty pictures of comets. So this is a comet you may not have seen. So if you remember last year, we had a really nice comet 2023 A3, I think, Shushinshan Atlas, which was a really nice comet. We saw it from here in October last year, big tail. This comet, 2024 G3 Atlas, is a sun-skirter comet. It was a very small comet that was discovered last summer by the Atlas survey, but it got very, very close to the sun. So it had a perihelion distance of about 0.09 astronomical units. It was debatable whether it would actually survive perihelion or not. In the end, it didn't survive. The nucleus was completely disrupted. So essentially, you imagine that you have this nucleus, which would have been sort of ices and dust. That was all basically thrown out as it went round perihelion. It broke up into a cloud of dust. What then happened was, as the comet was moving around, it left all of that dust trailing behind it, and it actually had a really spectacular dust tail with lots of structure as well. You can see various synchrones and syndynes in this tail, which is basically how the dust gets ejected from the coma. These were taken from South America. Unfortunately, this comet was really only at its best from the southern hemisphere. We didn't see much of it from here. But these are lovely pictures. I've just got a few more here. This is a lovely picture from Terry Lovejoy from Queensland, just showing a beautiful comet in the twilight sky. But what's amazing is that this comet, even though the nucleus itself was destroyed at perihelion, which was back in January, it's still visible. The dust from this comet is still there. And here's an example. You can see it very faintly, this image from Rob Kaufman. You can see where he's marked the ephemeris position of the comet, and there's a faint dust tail still visible in the sky. So just shows you that the dust that comets leave when their nucleus breaks up, it's still there, it just gradually spreads out. And of course, then if we're lucky enough to intersect that dust, it's what leads to the meteor showers that we see. But I said that this comet was only visible from the southern hemisphere. That's really true, but its tail was so big that it was actually visible from the northern hemisphere as well. And I went to Tenerife with the express intention of trying to photograph the tail above the horizon. And here's an example of a raw image I took. So the comet was low in the twilight. You may be able to see in that white box, very faintly, some streamers of tail. If you stretch it, you get this. And then if you really process it and stack lots of stuff, you get that. And this is the tail of that comet sticking above the horizon in Tenerife. Then what you can do is you can stick that onto a picture that somebody took in South America. So this is the main picture at the bottom there was taken by a photographer at the VLT in the Atacama. And his tail goes up, and then you can see where I could see the tail. And this is another thing that I'd like flat Earth people to explain, in that in the Atacama, the horizon's like that, whereas I was in Tenerife, it was like that. So how does that work, Mr. Flat Earth person? Anyway, I was really pleased to get that. It was predicted. I went out to Tenerife specifically to photograph it just after the last meeting, actually. Managed to get it. I mentioned Shushan Atlas. It's still there. It's actually coming out into the morning sky. And it's a pale shadow of its former self, but we're keeping the light curve going. It's got a very strange light curve, but not as strange as 12P, which Richard has already showed. So this is actually the BAA data on 12P. You can see these two outbursts that Richard mentioned post-perihelion, but loads of outbursts pre-perihelion. So I'm sure, Richard, there's good theories about why it doesn't do it post-perihelion, but it doesn't seem to outburst post-perihelion. And then I can see Janice looking at me now because we all need to get off to the pub. So I just have one final thing, which is a sort of comet, but not really. And this is something that people saw 2 nights ago. This is a propellant dump from the second stage of a Falcon 9 rocket. So it was launching a classified payload called NROL 69 into a fairly high orbit. The second stage propellants are kerosene and liquid oxygen. And the second stage obviously has to push the satellite into a high orbit. So the second stage stays in that high orbit. There are 2 things you need to do. One is you need to get rid of all the volatile propellants from the second stage to make sure that it doesn't explode and litter space with debris. And the other thing is that when you're doing that, you also do a deorbit burn. So the standard operation for these rockets is that they go up, and about 1.5 orbit, once they've deployed the payload, about 1.5 orbits after, they'll do a controlled re-entry. So the residual propellants are vented and at the same time the venting happens, you actually do a burn to reduce the perigee to the point that the thing will re-enter. And it happened that they did that over the UK just as it was getting dark. So at the altitude of the satellite, the sun was still shining. And so what you're seeing here is the kerosene and liquid oxygen vented out of the spacecraft, effectively then reflecting the sunlight back to us. There's a nice, this is sped up about 10 times. You can see there's a nice puff of activity here. After it left my camera field of view, it actually started doing the deorbiting, so it was actually spinning itself up for stability, which is why you get this spiral pattern, and then it fired its rockets to actually slow it down so that it would re-enter. But quite a lot of people saw this. It was a big thing on the BBC website. It's another of Elon Musk's gifts to us in the night sky, but quite an interesting thing to see. And a lot of my friends who were out just kind of walking the dog and whatever texted me saying, what on earth is this spiral galaxy thing in the sky? So I'm sure a lot of people saw it too. Anyway, that's that. Remember the eclipse on Saturday morning, and remember the April Lyrids coming up. Take a look at Jupiter and Mars whilst they're still in the sky, in the western sky, and let's hope for lots of clear skies. And as Mark said, you know, we all want light pollution to be reduced. So I think the onus is on all of us as astronomers to, whenever events like this happen, to sort of say to people, well, yes, we're kind of interested in looking at the sky and how light pollution makes that much more difficult. So if we can all kind of help with that project to get that message out there. So thank you very much. We're all going to go to the parcel yard, I think. So everyone's welcome at the parcel yard for a quick beer, and we can discuss whether comet nuclei are spherical or peanut-shaped.
Well, you can.
Thank you.
Thank you very much, Nick. Much appreciated. Any quick questions from the floor before we let him go? Oh, gentlemen, right. Sir.
That's good. That's the questions
you are holding a bunch of astronomers between here and the beer.
With the eclipse of the Earth, when you can see the grounding of the Earth around the moon or whatever.
Yeah.
In history, is there any record of that? And anybody suggesting that the Earth is round because of that?
Absolutely. Yeah, it was one of the sorry, the question is, so during a lunar eclipse, the shadow of the Earth that we see is round. And the question was, has that been used in the past as evidence for the Earth being round? And absolutely it is. I mean, people have known that the Earth has been round for thousands and thousands of years, and that was one of the pieces of evidence that they had, was that shadow was from the Earth and it was round. Well, certainly BC. I mean,
The ancient Greeks.
yeah, well, even older than the ancient Greeks, I think. But yeah, we're talking thousands and thousands of years. It's a complete myth that people in Spain that thought that Columbus was going to fall off the edge of the world because it was flat. Nobody of any intelligence in the Middle Ages thought the world was flat. Yeah.
Okay, well, let's call it a day there. Thank you very much again, everybody. Just make sure you've taken all your bits and bobs and any cups and glasses and whatnot. And I look forward to seeing you all again on the 4th of June. Am I right? Am I right? It's 4th of June. Okay. Keep well, and we'll see you in the parcel yard, those of you that can make it. All right.
Well, you see.
They're upside down.
Yeah. I went to a thing where a person had infiltrated a group of flat earthers, and he was giving a talk on all of the arguments that they use to justify their beliefs, and they were just bonkers.